In fact, today we want to talk, or maybe today we will talk about unlabeled data, supervised and unsupervised, and next time we will start with deep learning stuff. So I want to talk first about something we call it parametric model. So in a model, in machine learning, we try to build a model, and this model, in fact, it's a function, and this function has lots of parameters. So the difference between shallow learning and deep learning maybe will be the number of parameters, right? But at the end, it's parametric model. It's like regression model. When we have a regression model, we it will be an equation. The decision function will be an equation. For example, y equal mx plus c, where m is the slope of the line, c is the y-intercept. So it's a model, in fact. So the regression model, it's a model, and this model has number of parameters. So in machine learning, any models, we call it parametric model. So this parametric model, it's function that takes an image and return a class or label. We can use it for classification problems. Maybe we can use it for regression, for example. So the parametric model, at the beginning, we initialize those parameters with random values. And if we test the model after initializing it, it will give also some random label. So, for example, if we have this problem, cats and dogs, for example, if we build a model and we try to initialize weights with random values, at the beginning, when we give a picture, maybe we will get some random labels. And after that, we start the training process. And in this training process, we will try to readjust those parameters in a way to correctly classify all images, for example. At some point, those parameters will be at the optimal set value, which means that it cannot get better. So at some point, the model will be trained, and maybe retraining or keep training the model, it will have some negative consequences, not positive, because the model has already trained. So the parametric model can be used for regression, where we can also fit a model. So this is an example for classification. We have an image, for example, and we try to predict the label, for example. We can use it also for regression. This regression also, it's y equal mx plus c. Maybe at the beginning, we can just generate endless number of models if we can initialize m and c with random values. And after training, we will try to fit the model to the data which we have. So at the end, we can have a model which can be used for regression, for example. What are the types of machine learning algorithms? We have here in the outer circuit here, we have artificial intelligence. So in fact, artificial intelligence is a very general term. And underneath it, for example, in artificial intelligence, we can have an expert system. We can have black box models. We can have regression models, statistics, and so on. So the big umbrella, it's artificial intelligence. And underneath it, we have machine learning, for example. And this machine learning, we can get also something called deep learning, right? And the learning platform, or how we train our model, it could be supervised, it could be unsupervised, and also it could be reinforcement learning, right? So in supervised learning, we have labels, and we can measure the performance. So if you have label, for example, you need to train the model, so you have a cost function, and you can measure the performance of your model if we have labels. And the problem, it requires a huge amount of data, of course, and the computational resources. We need, you need a GPU, for example. If you have a deep learning, for example, and it requires huge amount of data, and it requires also time and computational resources. We have something called the unsupervised learning, and the unsupervised learning, in fact, labels are not available. We don't have labels. And this is the most, maybe 95% of data around us, it's unlabeled. Because all data in general, it's unlabeled, and we need someone to go and label it, for example. So annotation, for example. The nice thing in unsupervised learning, we can use it for annotating. We can use it to label an unlabeled data set, for example. In unsupervised, performance cannot clearly measure the effect. We can measure performance, of course, and somehow, but it's not possible to use it for training your model. And the AI task here is not very well defined. So, for example, in supervised learning, the task is very, very well defined. We have number of classes, but in case of unsupervised, don't have the number of labels, so the task is not very well defined. So the task in supervised and unsupervised learning is to cluster, label, and classify data. We have also another branch of machine learning. We can call it reinforcement learning. And in reinforcement learning, it's like we have an agent or a robot, for example. We have an agent, and this agent will observe the environment, and it will perform any task with maybe hit and miss or trial and error approach to maximize the success of its outcome. For example, we have an objective function, and in long term, in fact, we need to make rewards. We need to maximize this cost function or objective function in the long run. But in each step, in fact, it takes maybe, you can say it's random decisions. It could be at the beginning, it's random decision. So it will be maybe trial and error. And after that, it will try to select actions or sequence of actions which will maximize the objective function. So also reinforcement learning, very, very important area. So we can use it, for example, for games. For example, you can have an environment, right? This environment, it will be like simulated environment. For example, if you want to train, usually we use reinforcement learning for controlling systems or tasks, in fact. It's not just a classifying or regression, for example, but usually we use it to build a system which can behave in a smart way, or control system, robotic, whatever. So so in fact, we have this environment. It could be a video game, it could be game engine, whatever. We use this one for testing our model. We have an agent, reinforcement learning algorithm, or an agent, for example. This agent, it will try to sense the environment. So it will try to observe things, and it has maybe a list of sequence or actions, and it will select an action which can maximize the objective function on the long run. So, but usually we use it in control applications. For example, if we have a robot, for example, and we want this robot to find its way in a corridor, for example. So in this case, maybe we can use reinforcement learning. So it will start moving at some point. It will start move at some point, and it will maybe hit the wall. We don't need to wait until it hits the wall, for example, but we can sense the environment. We can get a signal that we have a wall here at some distance. So we can select another action. So maybe the set of actions, it could be go forward, turn left, turn right, for example. So imagine that we have 3 sequences. You can just turn left with some degree, turn right with some degree, and go forward. And we have a set of sensors, and we will sense the walls, for example. And we will select the decision or the action which will help us to achieve our objective at the long run. Maybe our objective is to reach this point. Maybe this is source. This point, this one, it's our destination. We need to reach this one as fast as possible. So one way, maybe you can just move like this one. Maybe it's a solution, but maybe it's not the best solution because it will take too long time to reach our destination, for example. So the model in this case, it will try to learn how to reach this goal as fast as possible. For example, it could be the objective function, it could be time or speed, for example. So, and of course, the reinforcement learning, it will try to select actions that maximizing its rewards and avoid actions that lead to negative reward, for example. So to solve reinforcement learning problems, it's just quickly. Maybe if we need to have 1 week later on, we can have 1 week for maybe some examples in reinforcement learning. But you need to construct the environment, such as game engines or other APIs. Because the problem here, if you want to train reinforcement learning algorithm with real robot, for example, or with an autonomous car, maybe it will hit a wall, maybe it will hit someone, it will kill someone. So it's not possible to train it using real systems. And it's much better to just try to reconstruct a game engine or a simulated environment for training your algorithms. And we have in Python, we have OpenAI. It has something called the GEM library that provide number of environments. I have been trying some of those environments last night. There are many things, in fact. So it's possible to have those and try to build an algorithm and develop training strategy, for example, to achieve those goals. So we have those stuff in Python, and even we can run those stuff also in Google Colab if you want. Yes. Today, I mean, the idea was to talk about supervised and unsupervised mainly, but we have been already talking about those. So the most important here to know that in unsupervised learning, it's less clarified, less defined the problem, and harder to solve. In fact, it's not easy to solve an unsupervised problem. Um, but when it's solved, in fact, the solution will be more powerful. Because the problem in supervised, we have set of labels. We cannot increase, we cannot change number of labels. So for example, if I have, for example, we have some cases, some images we need to classify, for example. So the problem is that we have a limited set of labels, and the output of my neural network also it will be limited because we need to have a fixed number of outputs. Number of outputs will be a number of labels, right? So if something happened in the future, for example, if we got a new label, for example, in the future, my model will not be able to discover it. But in case of unsupervised, it should be possible to discover new cases, new classes, new labels, and so on. So when we have a solution for unsupervised learning problem, in fact, the solution will be more powerful than supervised learning. So in fact, in supervised learning, it's a very well-defined problem. So we can call it, it's weak AI, right? But in case of unsupervised, it's a not well-defined problem. And when we solve it, we will have a kind of strong AI solution for it. Yes. Why labels are important? Labels are important because we use those labels for evaluating the performance of our algorithm. So supervised learning AI trains on data where it measures its performance using a cost function by comparing its predicted images with the true images, right? Labels guided the machine learning model or AI agent by providing it with an error measure. This error measure, it's the error signal which we use for training our model. We didn't talk about error backpropagation, but maybe also one time we need to talk about error backpropagation to understand how this. But it's very similar to a perceptron, for example. The problem for getting supervised data, it's expensive because we need to get someone to label data. So, for example, I have been working in a problem with students. It's predictive maintenance of road quality in Norway, for example, and we got lots of data, millions and millions of images from Staten Vivacen. So the problem data are not labeled, and we need someone to label it. And the problem we try to predict cracks on roads, and most of the roads are fine. So we need someone to search manually and try to find places where we have cracks. Of course, if you want to do it manually, it will be very, very expensive. It will take too much time. So one way for doing it is to use unsupervised learning, right? We can use an unsupervised learning to annotate areas which are different. And after that, someone will just go and annotate those specific locations. So unsupervised learning, in fact, it's a very, very powerful. Of course, supervised learning will be very good at classifying images of object which has labels, but it will be very poor at classifying images of object for which it has no labels, right? So if we train the model to differentiate or to classify images into cats and dogs, for example, and we have a monkey, it will not be able to discover that this image is for a monkey because it has been trained only for binary classification problem. It can just differentiate between dogs and the cats, but it has not been trained for monkeys, for example. So maybe it will misclassify monkey as a dog or as a cat, for example, if it is supervised. But if it is unsupervised, it will discover that we have a new class which does not exist before, in fact. And we just need someone to go into it and check that class and give it a label, for example. So it will have, so instead of having two classes, cats and dogs, it will discover that we have a new cluster. And this cluster is something which we don't know. The machine will not be able to know, in fact. And in this case, we need someone to go in and just say, okay, this class is monkey. So in this case, we created a new class which does not exist from before. So unsupervised is very, very powerful. Most of the majority of the world data, in fact, it's unlabeled. So with supervised learning, the ability of AI to expand its performance to never before seen instances is quite limited because most of the data in our life, in fact, it's unlabeled. So when you build AI using supervised learning algorithms, we will be limited anyway. We will be limited with the data which we used for training our models. But if we can go for unsupervised, we will not have this kind of limitations, and we will be able to solve really very complex problems. As I told you, maybe the machine, for example, if we are training models to discover vaccines, for example, or to discover kind of disease, maybe in the future we will get something different, not in the sets which we defined before. So in case of unsupervised, we will be able to discover those outliers. For example, you can just say it's outlier. Supervised learning will it's you can just say it's very well defined, or defined in a very narrow tasks for which we have well-defined pattern and not change over time. We assume that our data set will not change over time, for which we have sufficiently large labeled data sets. So for example, we trained a model to discover our faces while we are young, for example. We grow up, for example, or kids grow up. So at some point, maybe the machine will not be able to recognize them because it has been trained only with this kind of data set. But unsupervised learning will be able to adapt to unknown or constantly changing data sets, for example. So it will be able to, just because it's like an outlier, for example, if I trained a model for 10 classes and I have a new class, for example, right? So it will be considered as an outlier, and it will be classified as a new class, but we need someone to go in and try to give it a label. So after initial training, if the unsupervised learning find images that don't belong to any of the labeled groups, it will create a separate group for the unclassified images, triggering a human to label the new yet to be labeled group of images. So this is what will happen if you have an unsupervised algorithm and you try to classify images. Imagine it's family images, for example. I trained a model and try to classify family members. If you got someone who is different, so it will trigger the human. In fact, maybe it will put maybe like red circle, red rectangle around new faces, and it will ask the human or the user to try to annotate those images. And once it's annotated, it will be one of the labels which can be classified in the future. So this is very, very nice. And it's very similar to what has been done in Google, for example, or in Facebook. When you upload some images, it will try to classify people and try to find which one in the image, right? So it will annotate you. It will ask you, who is this person? And if you did it one time, it will be possible to annotate all images in the same class with the same name, for example. So we can have a label for the new class, for example. And if we have a new people appearing in those images, it will classify them as a new class, and it will also trigger the human to try to give a label to those new classes. So we will start with some supervised algorithms. So we have something called just an example, KNN. Do you know what is KNN?
Yeah, question.
Yeah.
Besides this learning methods, we have a transfer learning. What is it?
Yes, transfer learning. We will talk about it after deep learning. So maybe in 2 weeks from now we will have transfer learning.
It's some kind of unsupervised learning, or
no, it's supervised. In deep learning, we are working with supervised. So today we will talk about some examples, very, very simple examples. But in deep learning it's supervised. But transfer learning, for example, when you have been solving a problem, or you are solving a problem and you have very limited data sets, right? So, but you can see that someone has been using deep learning model for solving a similar problem. It's not exactly the same problem, but it's similar. So you can import his model and use this model and try to adapt it to your problem. We call it transfer learning. So don't need to start from scratch and initialize the weights from random values and start to training your model, because you don't have enough data. Maybe you don't have very fast computer, for example, you don't have a big GPU. So in this case, you can import a model which has been trained for solving a similar problem. It's not exactly the same. Maybe it's images, maybe it's time series, right? But it's different. So we can just make some small changes in the model and retrain the model using the small data, which you maybe not training the whole model, just to train some layers, for example, and try to customize this model into your problem. So we call it transfer learning. But it's within deep learning, in fact. And the deep learning, it's supervised learning. So for supervised algorithms, we can, thank you. We can take an example, a key nearest neighborhood algorithm, artificial neural network, and here also we can just say deep learning, right? Because deep learning also, it's supervised. So deep learning, it's supervised because deep learning, it's a kind of feed-forward neural network, right? So, but today we can talk about a key nearest neighborhood, and we can talk about, for example, artificial neural network as an example for supervised. For example, if we talk about key, and we have here a data set, it's in two-dimensional, 2x in x1 and x2. So each data point here, it's defined by x1 and x2, right? In this data set, we have two labels, two classes. One called the triangle, right? This is triangle, and the other one is a circle. Correct? So we have we have a data set. This data set, it's like this one, x1, x2. We have here some coordinates. And here we have the label, for example, or the target feature. So some of those data points are triangles, and some of those are circles. So we have two classes, right? And we need to build a model to classify it. So key nearest neighborhood, in fact, it's very, very simple. We need to define k, this factor k. So k, it's a number of neighbors, for example. So for example, if we selected k, and I have here a new data point. Do you see this one? It's a new data point. So this is new data point, and I want to classify it, right? How can we classify it? If you select k equal 1, for example, I will check the nearest data point to this point, only one, because k equal 1, and I will check this label. So the nearest one to this data point now, it's a triangle. So in this case, we will classify this new data point as triangle as well. So this one will be a triangle. So if you selected k equal 1, this one will be classified as triangle, correct? If you selected k, for example, equal 3, so in this case, we will check the label for the nearest three data points. So when we check k equal 3, we have one which is triangle, and we have two which is circle. So they call it's a measure voting. So in this case, two are circles and one is triangle. So what will be the label for this new example? So in this case, we will assign it to a circle, right? So if you select k equal 1, this one can be classified as triangle. If you selected k equal 3, this one will be classified as circle. It's a majority vote. So they call it majority vote. So we will check first for k equal 1. If you select k, it's hyperparameter. You need to select k by yourself. Maybe you can check it for k equal 1, 2, 1, 3, 5. It should be odd number all time. Why it's odd number? Because we need to vote for the label, right? I cannot select 4 because when it's 4, maybe we will have 2 circle and 2 triangle. So it will be hard to make a decision, right? So we need to select k all time equal odd number. So when k equal 1, we will check what I mean. We calculate, in fact, we calculate the Euclidean distance between the example which we want to classify and all data points, and we sort them from maybe small to high, and we will select the nearest 1 or the nearest 3 or the nearest 5, and we will have this majority vote. So if k equal 1, this one, it's the closest to this data point, right? It's very, very close to it. So we will check the label of this one. This label here, it's a triangle. So in this case, this one will be a triangle. We will assign a triangle to it. Because this is, imagine it's a cats and the dogs, for example. So we have this one, it's a new image. And the one which is close to it, it's a cat. So in this case, we will say, okay, this one is cat. Right? Okay, what if k equals 3? We will find the 3 nearest neighbors or the 3 nearest data points by Euclidean distance. And we will have this majority vote. We will count how many circles and how many triangles on those 3. So in this case, we find out that we have 2 circles, we have 2 circles, and 1 triangle. So by majority vote, we will assign circle to this data point. So now we can just classify it as a circle, right? This one, it's supervised because all time we are trying to look into label or target feature. So it's supervised. This algorithm is very, very simple one, but the problem in this algorithm, we need to keep all data points all time with us. We cannot get rid of any data points. So if I have 100 data points, I need to keep those 100 data points with me all time. Because in fact, the algorithm is not learning anything. It's just calculate Euclidean distance between each example and the 100 data points, and after that sort them in descending order, and the vote for a majority voting, have this majority voting, and after that we will assign a label to the new example according to this majority vote. So the problem here, we need big memory. So imagine that you have 20 million data points. You need to keep those 20 million data points with you all time. If you want to implement it in Arduino, for example, it will be a problem because, I mean, maybe you will not have enough memory for keeping all those data points. In addition to that, security issues. Imagine that we are building a model for patients in a hospital. So it's lots of information about a patient. So no one will allow anyone to carry and keep informations of patients with him or with her, right? Imagine there are customers for a bank. It will be the same problem also. No one will allow you to keep all data from the bank, for example, about clients or about customers. So the problem in this algorithm, it requires too much calculations each time, because each time I need to calculate the Euclidean distance between the new example and all data points. We need to keep all those data points all time with us. Each time we will calculate the Euclidean distance, we will sort them, and we will have this majority vote, and we will assign a label to each new example. But if you want to compare it with feed-forward neural network, no, I mean this feed-forward neural network, for example, it has 3 inputs. It has 4 weights in the hidden layer. It has 3 outputs. So how many weights here in this model? When we train this model, we have labels here. So maybe this one, it's a triangle. This one is a circle. So imagine that we are using feed-forward neural network. So this one will be much better because after training it, in fact, we will have only weights, number of weights. It will be 3 times 4. 3 times 4 plus 4. Here it will be 4 times 2 plus 2. So all number of weights here, it will be 3 times 4. It's 12 plus 16. So we will have 26 weights. So this is the difference between feed-forward neural network, for example, and the KNN. I need only memory to store 26 values if you will use feed-forward neural network, right? So I can train a model. I can train this feed-forward neural network to classify any complex problem. But all what I need, in fact, in terms of memory, is just a space to store 26 float values. Those are the weights and the bias. But in case of KNN, this is a very big problem because it's not parametric. This one, in fact, it's parametric. But this one, it's not parametric, right? We don't have any parameters. Right? We don't have any weights. We don't have any. We don't have anything, in fact, right? In KNN. So KNN, it's not parametric model. It's just an algorithm. It's just a way for calculating, for classifying new data points. So the problem here, we need to have a memory space for all data points. And imagine if you have million, 2 million, 3 million, it will be really very complex. And calculation, it will take so much time for calculations. Because if you have a new example here, imagine I have a new example here. I got a new example here. So I need to calculate the Euclidean distance between this example and all data points, between each single one, right? And after that, I will sort it in descending order. And I will select the nearest, for example, K data points to this one, and I will vote for label, for example. So the problem here, we do lots of calculations each time. In fact, each time I have a new example, we can make too much calculations, and we need big memory to store all those data points. And as I told you, maybe if you have memory, it's not allowed to keep those data points in your computer, right? It's not possible. If it is information of patients, if it is information of customers in a bank, for example, no one will allow people to store their informations and the data in their private computers or Arduino or whatever, right? So it's security and also it's memory requirements, calculations. So KNN, in fact, it's a very complex algorithm, but it's a very, very simple algorithm as well. So I just explained the KNN, how it works. So we look at K number, and this is integer number of nearest labeled points or neighbors, and vote on how to label a new point. When K equal 1, the algorithm is known as the nearest neighbor algorithm, when K equal 1. By default, KNN uses Euclidean distance to measure what is closest. So we use Euclidean distance. If it is in two-dimensional space, maybe also imagine that I have 5 features. So it will take also too much time for calculating Euclidean distance when it's in multi-dimensional space. The problem here, it overfits the data when K is very low. It overfits. Because maybe, do you see? It overfits. Maybe I have here, imagine that when K equal 1, I have this is my data point, and I'm using K equal 1. So this one, the closest is triangle, in fact, is rectangle or square. Sorry, the closest is a square. But in fact, I'm living in an area where we have many rectangles. So in this case, when K equal 1, this one will be classified, in fact, as square. But in fact, it's located in an area of rectangles. So it should be classified, logically, it should be classified as rectangle. So in this case, when K equal 1, in fact, the model usually overfits the data points. It will look into, it will just have this narrow vision. It will just look into the closest one, and the closest one, it's a square. So the data point will be classified as square, although it's in an area of rectangles. So the model will overfit the data points. Right? So for example, imagine someone is living in South Africa, for example, or maybe no, another example, he is living in India, and he has a neighbor, and his neighbor is from Norway, for example, and we are using a key nearest neighborhood to classify people, to classify nationality, for example. So we will check who is closing, I mean, we will use KNN algorithm. So according to KNN algorithm, his neighbor is, closest neighbor is Norwegian. So we will classify him as Norwegian. Although there are hundreds of people living around him from India, for example. So he should be classified as Indian, but because we have this overfitting problem, he will be classified as Norwegian, which is wrong. So this is a problem. So KNN is lazy algorithm, meaning it does not need any training data point for model generation. We don't generate a model, in fact. We don't have a model, we don't have any parameters. So there is no parametric model here. KNN, to classify a new data point, it needs more time to scan all data points and more memory to store and sort all data points. We need to scan, we need to calculate Euclidean distance, we need to sort, and after that we need to check for label. KNN perform poorly when the number of observations and features grow and they become computationally inefficient. If you are calculating Euclidean distance in two-dimensional space, maybe it's fine, but if it is in 3, 4, 5, 6, 10, it will be really very, very complex. Number of neighbors is hyperparameter that you need to choose at the time of. Sorry, we don't build a model at the time of solving the problem, right? So you need to select K. Maybe you can select K equal 1, maybe 3, 5, and after that check performance, which one will give you better performance. But remember, when K is small, when K is low, the model will overfit your data points. KNN is used to recommend, predict what the user will like in Facebook Friends, for example, Google Search, Amazon Shopping List, and so on, right? Because we calculate Euclidean distance. So for example, if I like some kind of friends, for example, maybe it will try to predict, recommend movies. For example, it calculates Euclidean distance between my choices and the other movies, for example, in the data set, and it will try to recommend a movie to me, for example. So So I mean, we just so in fact it works in those three steps. We calculate Euclidean distance or Manhattan distance. You need also, I mean, what kind of formula here for calculating distance? It's a hyperparameter. So some people use Euclidean distance. Maybe some people using Hamming distance. Some people use Manhattan distance, right? So how you will calculate distance between your data point and other data points? It's a hyperparameter. You need to select it. Find the closest neighbors. You need to select k, which is hyperparameter. We need to select k as odd number because I need to vote for majority label, for example. So I need k to be just odd number. And after that, we will vote for labels. So this is an example here. If you select k equal 1, this data point will be classified as star, right? If you selected k equal 7, it will be classified as a star as well. Yeah, so first we have those data points. We need to keep all data points with us all time. When we have a new example, we calculate the Euclidean distance between this example and all data points, right? We will sort, and after that we will vote for, we will select the k, and we will vote for labels. KNN, I have an example here. It's we can use key neighbors classifier from sklearn if you want to use it. And I'm using it with Iris dataset. Iris, we have 3 labels, right? We have 3 classes, and I want to use key neighbors, KNN for classifying it, for example, to make comparison between it and a perceptron or feed forward, for example. So you need to use key neighbors classifier from sklearn.neighbors. We split the data into training and testing, right? And I'm selecting here k equal 5. It's hyperparameter. And by default, I guess by default in KNN, we use Euclidean distance. So that is why I didn't select here Euclidean distance. If you need to select different distance, you need to select it here. So now we are testing it for k equal 5. And from last week, you can build the pipeline. And for example, you can use grid search. So grid search can help you to select maybe between 1, 3, 5, 7, 9, right? And check the performance of your algorithm, for example. So we will fit, I divided my data, split my data into training and testing, and I use as a training for building the model. But just remember, it's not building, we don't build any models, right? We don't build a model. And after that, we will use it for predictions, right? And after that, we can check accuracy. So in fact, this figure, it's for k equal 1. We have accuracy equal 93%, right? When k equal 5, the accuracy is 95% or 96%. When k equal 9, the accuracy is 93% back again. So maybe better accuracy is for k equal 5. And of course, if you want to plot the decision boundary, it's easy. I mean, we did that several times. We have this one, it's x1 and x2. You just need to generate this grid and send all those data points to the model to predict labels if you want to plot those areas, right? Yes. Do you want to go to the example code and check it? Should we go to the example and try to, or should we just go ahead?
I have a question.
Yeah.
So in the case, for example, that you have some data that you really do not know the labels, if you want to build these clusters of neighbors, how would you then check for the accuracy?
We need to select another, so your data set is unsupervised.
Yes.
Okay, when it's unsupervised, we will pick an unsupervised algorithm.
Okay. Yeah.
Right? So the unsupervised algorithm, in fact, we will use the features for classifying it. Do you know, I will give you a very simple example. Do you know coins? Do you know how many coins we have in Norway, for example?
How many what?
Coins.
Ah.
So you have 20, you have maybe 5. We have 5 krona, or we don't have? We have 5. We have 2, right?
Yes, 1.
So when you put it in your hand, can you discover a label for? Can you discover that this one is 20, this one is 10, without looking into it?
Sometimes they have some characteristics, yeah.
No, without touching. Just put it in your just put it in your hand. For example, you feel the size, you feel the weight. Correct?
Mm-hmm.
You feel the size and weight. So in fact, from the size and the weight, we can classify it into exactly. It's unsupervised. But if you have bag of coins, just by touching it, in fact, putting it in your hand, you can just classify it. This one 20, this one 10, this one 1, this one 2.
Okay.
So how we do it, in fact, we do it by maybe the size and weight. Correct?
Okay, yeah.
Size and weight, not label. So size and weight, there are feature of each coin. Correct?
Yes.
So so you can just classify it. So for example, imagine that we have someone who is blind. We will give him all those coins. He will try to cluster them without looking into it. Just by weighing it by his hand and the size, he will say, okay, this one looks bigger. He will make maybe 4 clusters or 5 clusters. And after that, we will ask someone to look into the data after sorting, after clustering it, and we will ask him to give a label. He will look into it, okay, this one is 20, so this group is 20 krona. This one it's 10 krona, this one is 5, this one is 2, this one is 1. Right?
Yeah.
So this is how we will work with unsupervised programs, unsupervised learning. We need to select some features, and those features, we hope that those features will help us to classify it without looking into the label. And after clustering it, we will give a label.
Mm-hmm.
You will look into it and you will say, okay, all coins which belong to this group will be 20 krona. Because by the way, if you weighted it, it will not be exactly the same. Because for example, if we have a coin from 20 years and a coin from 1 year, if you weigh it, in fact, it will be different. So there will be some difference between both of them, but they will be located in the same region, for example. And after that, if we have a new coin, we will just calculate maybe the Euclidean distance between this one, the new one, and the other clusters, and the closest one will be this one. It will belongs to that one, which is closer to it, for example. So we will have an example. We will have an example very soon.
Okay, thank you.
Can I also ask one thing?
Yes, please.
Is this basically the k-means clustering, or are these different things?
Yes, it's k-means clustering.
Okay.
Yeah, this is exactly k-means clustering.
Yeah, because the naming is different. So I was like, is it the same thing?
No.
Or?
Yeah, we have KNN. It's a key nearest neighborhood. Key nearest neighborhood, it's supervised. But KMC, key means clustering, it's unsupervised. So we have 2 algorithms. One called the KNN, one called the KMS, right? So this one, it's a KNN. KNN, it's supervised, but the other one, it's a key means clustering. KMS, KMC.
Mm-hmm.
Key means clustering, KMC. So KNN, it's supervised, but KMC, it's unsupervised.
Okay.
So when it's unsupervised, we don't care about labels. We don't have labels. We will work with the features of the data. So they're similar to the coins. If you have coins, for example, maybe you can just use a size, maybe radius or the size and the weight of each coin. And using those 2 features, we can classify them. Yes.
Sorry, a quick question, if possible.
Yeah,
on those images and figures, what are the backgrounds? The background colors? We have purple and then dark and light green.
This one?
Yeah.
Maybe it's purple, maybe it's a green and yellow.
Yeah, but what do they represent? I mean.
Oh, why? How can we do it?
Yeah, I mean, what are they? Why do we have those colors?
Okay, because this one it's iris data set, and in iris data set we have 3 classes.
Yeah. So I think maybe the first figure is maybe for k equal 3, because it does make sense that it's for k. If the background colors represent the points in the grid where it would be classified as a corresponding class, I doesn't make sense that you would have this type of image, I think.
No, K here, it's not KNN, it's not number of clusters. It's a number of neighbors.
Yeah. So if you see this small dark green tail that you have between, that one, yes.
Oh, this one?
Yes.
It doesn't. Yeah, maybe it's not one. Yeah, maybe.
Yeah. Okay.
But maybe it's correct. But when I'm plotting it, I'm not. I selected, for example, equal axis, right? So when it's equal axis, the distance will look like longer or larger, but in reality it's not.
Right.
So I'm just
yeah.
So just please try to be sure about it.
Yeah. I didn't think about different distances.
Yes. So here we have one class here. We have here.
Ask a question too?
Yes, please.
In neural networks, we have weights as an output of the model. So here we don't have any models. What is the output? It's like when we feed the KNN model, it's like, what is the output and how do we perform tests on this on non-parametric model?
But remember, we
have any parameter. So what does it have?
Yeah. In reality, it does not have any. It does not parametric model. But this function in Python, for example, I know this function predicts and fit. For example,
let me ask it in another way. In these figures, there are some boundaries. It's like purple and yellow. And
yes, this is correct.
How do we figure out these boundaries? How do we find out?
Okay. So imagine that. Do you see my this point? Imagine this one. It's a new example. I will calculate the distance between this point and all other data points. Right? If k equal 1, for example.
So the KNN model always has all the data?
All data, you must have all data points with you all time. This is a problem in KNN. And each time you need to calculate a clean distance and classify each single point according to this strategy. So in fact, it's approach. It's not a model, but it's way of solving a problem or a method, for example. But it's not a model. We don't have a model. So even in Python, I don't know how they wrote this function for fit.
We don't have parameters because it's
no, you don't have.
Yeah.
We don't have any parameters. We don't have any model. So we need to keep all those data points with us all time. But I don't know, in fact, how they build those functions. Because in reality, we should not have any fit. We should not have this one. We can predict directly without fitting this one, because we are not building any models. So because in fact it's just we predict all time because we don't build any models. So how can we generate those decision boundaries? I mean, as I told you, we divide this one into a grid, and we predict the label of each point here, right? So for each new point here, we calculate the Euclidean distance between each point and all data points, and sort, and after that vote for label, and we will decide that okay, this one belongs to this label, this one will belong to yellow, this one will belong to purple, and so on. So I can share my screen with you to see the code. Can you see this one? I will open it in Colab. So we have this key neighbors classifier from sklearn. So we need to run the part. And this is the data points. This is iris data points. I'm selecting only 2 features. So I'm selecting, in fact, feature number 3 and the number 4, right? So we have here one class, another 3 classes. We have 3 classes. This is very clear. But maybe plotting it, you need to maybe select, I mean, we have some overlap here between some data points. So here I'm running it for k equal 5. So the accuracy is 93%. In fact, maybe I can try it for 3. When it's 3, so the accuracy it's 93%. When it's 7, maybe 93%. When it's 9, no, I have maybe, I don't know why it's maybe when it's 1. So when it's 1, it's a 95% accuracy. And after that, for plotting those decision boundaries, I need to generate some values for x1, for example. So I'm just selecting all values between x1 minimum and x1 maximum. And I subtract -1 and add +1 here, plus 0.1, just to be sure that that I'm covering all the range, for example. So I'm generating all data points here for x1, and the same for x2, and I'm using x1 and x2 to generate a grid, and I'm using all those grid points for with a model to predict which class they belongs to. So it will be like this.
Can you decrease the step size of the range in MP range? Yeah.
Is this one?
Yeah. Can you decrease the step size to see it's for the grid? Yeah.
Like this, for example?
Yeah.
It will take more time because we will generate more much bigger grids. Yeah, it will be like this. It looks more beautiful, right?
Right, but it's the same. It's a line again. It's again a line. It's not...
Yes, it's a line. Yeah, of course. Yes, this one it's not line, in fact, but just I mean we generate the grid and we send all those data points to the model, and the model will calculate the Euclidean distance between each point and the whole data points, and it will classify this one into one of the 3 classes which we have.
What will happen if the distance, for example, I'm looking at this border between the purple and the green. What will happen if the distance is the same? Like if there is a green point on the same distance as the blue point?
It would be exactly the same. Yeah.
I mean, I don't know.
Yeah, maybe. I mean, so, for example, if the distance is 1, 1, 1, for example, and the two of those were class 1 and one was class 2, so it will be classified as class 1, right? So when we are sorting, I mean, this is how the sorting function works. So we will sort those Euclidean distance in descending order, for example, right? In ascending order, because we need to start from small to big, right? So if the distance was 0.1 and after that 0.5, 0.5, 0.6, and we're selecting k equals 3. So we will check the 3 neighbors with distance 0.1 and 0.5 and 0.5.
What if k is 1?
This is easy, right? Because when k is 1, we will select the nearest one, for example. If the nearest one, and we have 2 equals 0.5, I don't know which one will be selected. We need to check sorting function, how sorting function works.
Select it randomly without, yeah.
Maybe it will select one random. Yeah, because both are the same distance, so it will select one of those.
Or maybe the last one, it's like overwriting the...
So we need to check how sorting function is implemented. So, but you can go you can go and play with the numbers here, because it's, of course, it's strange. We should not fit a model here, in fact, right? What is effective metric? Is it Euclidean distance?
I know that just for whatever we use is distant additional parameters. Yeah.
Yeah, we use Euclidean distance. So if you want to change it.
Yeah, I checked this, and it's so strange because the default distance is Minkowski with parameter with P2, which is essentially Euclidean. And I'm so confused about this background tail for and neighbors equal 1. I don't know why.
This one.
Yeah, I don't. It doesn't make any sense. I think maybe the painting of the background is not.
Yeah, but we can select, for example, another 2 features. Maybe this one will be also more complex. Maybe you can make, okay, it will take some time. Do you see? Now we are selecting 2 different features. But k equal 5, right? No, k equal 1.
1, yeah. So I think something is wrong with the background, because clearly you can see those brown dots that have green background. That doesn't make it's not right. Yeah.
Yeah. But maybe just a blotting, because this one, it's not. Maybe we need to blot at equal, because it looks this one from 0 to 9, this one from -5 to 3, right? So if you can make this one equal axis, how can we make it in Python? How can we plot an equal axis?
Did you change the features too when you are predicting? Because I think we just changed in the
no, we just need to maybe plot it one more time with equal. Is it any way to make it easy? But maybe you need to just make some changes. Can you try to? Do we need to define axes here? But I didn't define axes, so maybe it will not work. No, axis is not defined. Yeah. So yes, we just need to try to plot an equal axis. So try to fix this one.
Yes, I think it's a good excuse to read a bit of documentation about matplotlib later on.
Yeah. Yes. Okay. So maybe we can do it in the break. So I mean, maybe we can take some maybe 5 minutes break or 10 minutes break, and we can go back to unsupervised algorithms, because in unsupervised we need to talk about k-means clustering, and we need to talk also about maybe principal component analysis. We'll talk about it already last time. Maybe we can talk about autoencoder. So autoencoder, it's also technically it's supervised, but it's unsupervised because we are not working with data. But maybe the most important is to talk about k-means clustering, and to know how it works. So so should we take maybe we can meet again at 10:15, for example, after 11 minutes. Yeah. Okay, so thank you very much. We will meet again after coffee break. Bye-bye.